All right, so today we're starting chapter 4, day 1, which is linear functions. If we look at the top of the page, you're going to notice a familiar formula, which is the slope-intercept form. Obviously, the m is the slope in this form, b is the y-intercept, but what we're going to notice in our honors pre-calc class here, there's going to be a lot more applications in using word problems to create equations in linear form or a linear function. So a couple things to note about the y-intercept is, remember, slope is a changing value, so the cost per amount of item. The y-intercept is your initial cost or initial value. Remember, because it is the initial part, this may be the cost when t equals 0, t being time typically. And again, initial, it could be a starting fee. So again, now that we're in honors pre-calc, you're going to read a lot of word problems, interpret it. You need to recognize what the starting value is and then what is the cost per item. So on the right side, we notice c of x. This is just the function notation of the same thing. If I wrote right above it, y equals mx plus b, right? Or y equals mx plus lowercase b. Essentially, this is the same thing where c of x is just the cost. That is the y value. Again, a would be our slope. So c of x is the cost function. A is the marginal cost. So one thing to note again, if you compare the two, the capital A is the same as m. So it's really important to know that that is the slope, or if we're talking about cost, it is the cost per unit. Okay. B is the cost when the time is 0 or when the starting amount is 0. So again, your initial cost if you didn't have any of each. Okay. Slope, another word, and this is going to be really important as we move forward through this semester. Slope can also be known as the rate of change. Okay. We're going to find out later that a rate of change doesn't have to be linear. We're going to talk about average rate of change, which is the average slope across from 2 points. But for now, just understand that the rate of change is the same as the slope between 2 points. And then just remember that the formula for this is the difference of y divided by the difference of x, or your algebra 1 stuff, y2 minus y1 over x2 minus x1. If we're talking about the problem-specific words that we might be seeing in our word problems here, one word you might see is the steepness, velocity, marginal cost, or the word per. So these are some of the problem-specific words you're going to see. Obviously, steepness would go with the slope. We already talked about marginal cost being tied to the slope, the word per. And then again, the velocity is the average rate of change or the rate of change over time. You guys have seen these in the past, so just remember when you're writing equations, standard form is ax plus by equals c. Slope-intercept form is your y equals mx plus b. We already saw that up top. Point slope form is your y minus y1 equals m times x minus x1. Couple things about linear regression. If we're talking about a linear function, we're going to notice in a problem later in these notes and on some of the homework that if you look at a bunch of data points, you can get all these data points that have these outputs. Okay, so a scatter plot are a bunch of data points from an experiment or a study that may have a correlation. So a positive correlation would mean that these data points, if you were to draw a straight line through the average amount, we should take away these end ones because those are extremes. If I drew a straight line cutting the amount in half, you would notice that it has a positive correlation. Over time, whatever the y value is, the y-axis represents, it is increasing. It has a positive correlation. On the contrary, if we had a different experiment or a different study with a bunch of data points on a scatter plot, you would notice that as time goes on from left to right, the correlation has a negative correlation. It is decreasing over time. Okay, so you notice on the first one we have over here, it's kind of a circle. It's neither positive nor negative because you could draw a line either way. But you can see on the second and third one, it's kind of clear that if you drew a line cutting them in half, you would get that positive and negative correlation. So, as I mentioned before, a lot of this stuff, at least the basics for the math part, are coming from your Algebra 1 and Algebra 2 classes. So, for example, number 1, it says find the linear function that satisfies the given conditions. Well, we already know that our function notation tells us if f of 3 equals 2, that tells us that at the point x, the y value is going to be 2. And then for the second function notation, it tells us another point that at the point x is negative 3, that will have a y coordinate of negative 4. Be careful. It's a little tight there, but there is a negative there. So if we're going to think through this, we're essentially finding a linear function. So we're trying to write an equation that satisfies the line that goes through both 3, 2, and negative 3, negative 4. So think back to your Algebra 1, your Algebra 2. How do I write an equation, a linear equation, that goes through those 2 points? Go ahead and pause the video and then try it out on your own, see if you can come up with it, and then go ahead and unpause it when you got your answer and see if it got it right. So as we go through this, down here we had those 2 points. We first had to find the slope. You cannot write a linear function unless you have the slope. Because it's a linear function, it has to have a slope. So you take 2 points on that line, find the slope. We found that the slope was 1, and then we could either write it in our point slope form or our slope intercept form. Remember, because they didn't give us the slope intercept, the y-intercept, you have to put it in point slope form first, and then distribute the slope and get y by itself so that it's in slope intercept form. Okay. On the next page, let's go ahead and check out part B. I'm sorry. So now we're finding the graph of the inverse function that passes through these 2 points. Okay. So similar concept where they're giving us 2 points on a linear function. However, because it's talking about the graph of the inverse function, we're trying to find the linear function where the inverse of that linear function passes through those 2 points. So these 2 points are on the inverse of our function. We're trying to find the original, the non-inverse, right? The normal function. Well, if we remember the way that you find an inverse, or what it means to invert a function or any type of function, is you switch the x and y. So if the inverse function has an x and a y, we'll call them x1, y1, and x2, y2, right? Those are 2 points on the inverse. Well, then the original function, because it's the inverse, correct, then these coordinates would just be flipped. So since we knew 2 coordinates on the inverse, and we know it's the inverse of our blue function, we now know 2 coordinates. Let's stick with blue. We now know 2 coordinates on the original function. Okay. And then just by doing that, we can go ahead and again, in order to find a linear function, we have to have the slope. So we can use the 2 coordinates that we know are now on the original function. So there's our slope. And then we can either put it in point slope which I believe the easy one would be using the 4, 0. So that's our point slope form, or slope intercept. This one's actually nice because it's kind of already in slope intercept form since 0 is on that side. So all we have to do is distribute that 1/2, and there we go. So again, they give you 2 points on the inverse function, and because we know that the inverse is the flipping of x and y, we can do that with each individual point, and then we know 2 points on the original function, or the non-inverse function. So now moving down to number 2, here's where we get into those word problems and interpreting kind of what's going on. A manufacturer buys a new machine costing $120,000. It is estimated that the machine has a useful lifetime of 10 years and a salvage value of $4,000 at that time. Okay, so a couple things just to look at real quick. We know that the initial cost of the machine, or the initial value, because it says it's being bought new, is $120,000. And then the salvage value is $4,000. And here's where you got to look closely. It says at that time. Well, at what time? Well, let's look back. It says after 10 years, it has a value of $4,000. So as we're kind of processing through this here, let's think about how we can write a formula for the value of the machine after t years, when t is from 0 to 10. So if we're thinking about this in terms of a coordinate, right, the x value would represent time, and the y value would represent the value of that machine. So just by thinking about our formula in terms of those coordinates, we can start breaking down the information that we know. Well, we know that the initial value at time 0, because that's when you buy it, no time has passed, we know that the value is $120,000. So that's one value in our formula. The other value, or the other coordinate, would be after 10 years. So 10 years down the road, it has a salvage value of $4,000. Now, just like we had up on the last problem above and the one on the previous page, we have 2 coordinates. We're going to make a linear function using these 2 coordinates. In order to do that, we need the slope. So we can do, the slope is 4,000 minus 120,000 divided by, let's go 10 minus 0. We get negative 116,000 over 10, and the slope would be negative 11,600. Oops, sorry. Which again, thinking about this in terms of our word problem, what does it mean? Well, the slope represents the change in cost, right? The slope, or the marginal cost, is what's happening per year, because our x value is time. What's happening per year? Well, if we bought this machine at $120,000 and it is going down by $11,600 per year, then over 10 years we should end up with $4,000. Now, if we're trying to write the final formula representing the value, so we'll go ahead and use v of t. You can use c of t, you can use f of x, or f of t. We should be using t because that is our variable, but they didn't really specify the other part. So we'll use v of t. That's the value of the machine over time. We got to write this linear function. Well, we have the slope, so we have a couple options. We can either do point slope, which is what we did on the last one, or what's nice here is because we know our initial cost, this is our b value, or the y-intercept. So we can just write v of t equals our slope, t. Don't forget that our variable is t, not x, and then plus $120,000. So again, remember, this is just a very word problem way of saying y equals mx plus b, right? We know that our cost is, or the initial cost is $120,000. That's our b value. We know that the marginal cost, or how much it's changing per year in this case, is it's going down $11,600. And then the v of t represents our y value. What's the value at that point in time? Which, if we look at part B, lucky for us, we're actually going to use this information. So for part B, it says find the value of the machine after 8 years. Well, we know at time 0, where we first bought it, it's $120,000. We have this formula that can help us find the value of that machine at any point in time after we first bought it. So all we have to do here is plug in 8 years. So we plug that in. And when we do that, the cost, or the value of that machine after 8 years is $27,200. Which again makes sense, because if we just went 2 more years, that would be 10 years, right? Then we would lose another $23,200, which would put us at our $4,000 value after 10 years. Okay. So again, kind of very similar. If we look at number 3, suppose that the cost to a manufacturer of producing X units of a certain motorcycle is given by that function, that cost function. C of X equals 220X plus 4,000, where C of X is in dollars. Go ahead and pause the video at this time, and you can find parts A, B, and C. Okay. So now, if we go ahead and continue, hopefully you tried it. It's asking to find the marginal cost. Now again, if we looked on the front page, we already talked about what the marginal cost is. The marginal cost is essentially the slope, right? It's the value per unit. So if we just look at our function here, we can tell that the slope is $220 per motorcycle in this case. Okay. For part B, find the cost of producing 500 motorcycles. Well, we already said that because X is the number of units of a certain motorcycle, we can just plug in the 500 for X, and that would give us the cost if you had ordered 500 motorcycles. So by doing that, we go ahead and plug it in, and we find out that the cost would be $114,000. Now, for part C, it says using parts A and B, read very carefully. It says because you are using parts A and B to find the cost of producing 501 motorcycles, we cannot, we have to read the instructions carefully, we cannot just plug in 501. Now, if it didn't have that part to the instructions, you could just plug it in. However, because it says using parts A and B, we have to think and we have to show our work that we are using parts A and B. And by doing this, we notice that since we're looking for the cost of 501 motorcycles, right? We know that that's just the cost of 500 motorcycles plus the cost of one. So in doing that, we notice that the cost of 500 motorcycles is $114,000, and the cost of one would just be $220,000. So we can add them together, and the cost of 501 motorcycles would be $114,220. Okay, it's very important that we show this work, that because it expressed in the instructions we're using parts A and B, that we follow through on that. Okay, awesome. Now on the next page, for number 4, they're giving us some data points. So we had talked before about a stat plot. So what we want to do here first is all they're giving us is the data or the experiment or the study or whatever was kind of going on. Luckily for us, they had already scaled the X and Y axis, so we don't have to scale that on your homework. I believe you will need to identify the scale. You can go up by 1, you can go up by 5, you can go by 20. Just recognize the data at what the best scale would be. So first thing you want to do is whenever you get a table, a lot of times we talk about years would be your x-axis or your independent axis, and whatever the other thing is, whether it's cost or in this case natural gas production, value, whatever, would be your dependent axis, the y-axis. Okay, so by recognizing that, we can go ahead and plot these points. All right, so kind of like we talked about before, what we're trying to find here is the regression line. Okay, when we look at these data points, lucky for us, we have our calculators, so those are very nice. A couple buttons you're going to hit: stat, then edit. Okay, so you're going to hit stat, then edit, and I'm going to show you this in a minute. But it's important that we make L1 your X values, so the first row, L2 the Y values, okay? And then after that, you're going to hit stat, calculate, or calc. Then you're going to hit lin reg. So you're going to scroll down, and there's going to be a lin reg, a quad reg, maybe a cube reg. There might be a couple other ones. And then after that, you're just going to hit calculate. And what this is going to do, and we'll show this in a minute, is it's going to output your A and B value in slope-intercept form. Okay. Here, we'll show you how to enter these into your calculator so you can get that linear regression line, or the line of best fit for your data. So again, what you got to do is you got to hit the stat button here. Then you got to edit your list. And as we noticed, again, L1 has to be all of your X values. So when we go through these, you type in 0, enter, 1, enter, 2, 3, 4, 5, 6. And then in your L2 column, remember we talked, these are your Y values. So when you go through it, you're entering all the Y values. Make sure, be very careful, make sure that the amount of data is the same, right? If you have 10 X values, you should have 10 Y values, okay? And then after that, what you're going to do is you can clear back to the main menu, or you can hit these next buttons. It doesn't really matter. But you're going to hit stat. You got to go over to calculate. We already input our list. So you're going to scroll over to calculate. And then down here, we're going to go to a linear regression. Okay, so again, this is telling us we're going to get it in AX plus B form. Make sure that your X list is L1, your Y list is L2, because that's what we had set it as. And then go down to calculate, hit enter. And then again, what this does is it takes the data and it finds the slope for all the data, the best slope to represent the data points, and the y-intercept. And now we have our line of best fit from the calculator, and it said A equals 1198.04. and B equals 71345.89. So that means that our line of best fit would be this. And this is our linear regression. This equation, or this function, this linear function, best represents this data on our graph, or this table. So if we want to draw this line, we can be as specific as we possibly can. This would be our y-intercept, right? If we find that point on the graph, and we're going up approximately 1198, so that's up about 1,000, 1,200, about 1,200. So go up about 1,200, and then over 1. So we go up about 1,200 and over 1. No, that's the wrong column. Hold on. So this one would be 71,000. So we go up about 1,200 and over 1. And then we go up about 1,200 again and over 1. Up about 1,200 again and over 1. And again, as long as you have the equation correct, if the numbers aren't exact, you can do the best you can. And by doing the best I could, we noticed that that line does go through about as close to half as it possibly can. Okay. Again, use a straight edge. I don't have a straight edge here, but always use a straight edge when you are graphing. Okay. So down to part B. Okay. What are the units associated with the slope of the regression line in part A? Okay. So again, this is understanding what you're graphing, what your graph represents. So if we look back at the original, what units are associated with the slope of the regression line in part A? Well, our Y values are in TCFs, or the trillion cubic feet. So it's how many trillion cubic feet are happening per year, right? So this would be TCFs per year. Okay, what is the natural gas production in TCFs per year? And that's the unit. Okay. For part C, use a regression equation to estimate the production in 1999. Actual productions was 83,549. Is our estimate high or low? Well, if we know that this started in 1990, we'll use green here. We know that this started in 1990. That's when this data started being collected. We can say that after 9 years, we'd be in 1999. So we'll do 1198.04 times 9 years later plus 71345.893. We'll go to 3 decimals, try to be exact as we can. Plug that into your calculator. You get 82128.217. So based on our data from 1990 to 1996, I guess, right? We did 6 years of data. We guesstimated, or we could hypothesize, that the gas production in 1999 would be 82,128. Well, they told us that the actual production was 83,549. So obviously our prediction was low. Okay. Now the second part is we want to compute the percentage error. Okay. Well, so the percent error is the absolute value. We'll write this equation down. I believe you guys did this in Algebra 2. If not, go ahead and write this down so you have it on file. Percent error formula is the exact, right? So what actually happened minus the estimate of what should happen. Those are in absolute values, divided by whatever the exact was, okay? And then times 100. So if we do that, we could do 83549 minus, that's what the exact was, 82128.217. Could put them in exact values, but it's going to be a positive number anyway. Divided by 83549 times 100. And you notice that the percent error was 1.7%. So our estimate was 1.7% off from what actually happened. Now, obviously, depending on what field you're in or what you're calculating, that could be good or that could be really bad. I mean, this is talking about natural gas production. So if you're 1.7% short, right, we were low, there might be a lot of problems with that depending on who's using this gas and what needs to be done with it. But in other cases, 1.7 might be pretty close. It might be a pretty good estimate. So, but that's the percentage error. Now, if we look down at number 5, we're going back to using rate of change. So for number 5, we have f of x is ax plus b, where a is not 0. So it's just telling us the slope is not 0, which makes sense because then that would be a constant function. And then the same with g of x. We're finding the average rate of change given of the given function on the interval AB. So we're finding the average rate of change over AB. So first thing we got to find is the actual function itself, right? So they're giving us the function, the inverse of f of g of x. So we're finding the inverse of this composition function, okay? So if you remember your order, PEMDAS, well, we're going even further now for functions. We always want to do the composition first, and then we can do the inverse. Then inverse. And then we have to do the average rate of change. Okay, so we got a lot of things to do here. Let's go ahead and start by doing this composition. So just finding f of g of x, if you remember, plug in from right to left. So I take the g function, plug it into the f function. So we would take c of x plus d, plug it in for x in the f function, and we have a times cx plus d plus b, and then we can go ahead and distribute that out. So f of g of x, this is the function. And actually, you know what? Let's just call this y for now, because we're going to be finding the inverse anyway. And we said when you find the inverse, you switch x and y. So let's just call this y, make it simpler. So we have y equals acx plus ad plus b. Okay, so this is f of g of x. That's the function. But now, and we can write this in another color too. Let's go red. We got to find the inverse of this function. So now we have to find the inverse. We already know when you find the inverse of something, you're switching the x and y. So when we switch the x and y, we have x equals acy plus ad plus b, and then you got to get y by itself. So when we go ahead and do that, we have x minus ad minus b equals ac, y, and then we got to divide everything by, let's go green, divide everything. It's going to make it easier when you're plugging in, if you divide everything by that. So let's go ahead and pause for a minute here. You don't have to pause the video, but if we take a minute to stop and see where we're at, we have just found, we'll put it down here, we have just found the inverse of this composition function. So that's what we found. Okay, we did a substitution, we did that composition, then we found the inverse by flipping x and y. So the inverse of f of g of x is x over ac minus, the a's cancel, d over c minus b over ac. Okay, now we're not done yet. Make sure you're always answering the question. If you get stuck, reread the question, see what you're actually trying to find. But remember, what we are trying to find is, let's go ahead and use a highlighter here. Let's have some fun highlighting. The average rate of change of that given function. So now we have the given function. We're finding the average rate of change of that function over the interval a to b. So we remember that the average rate of change is evaluating the function. So let's say we had f of x. Let's say we had f of x over ab, right? The average rate of change would be f of b minus f of a over b minus a. So all we have to do is we have to plug in b into the function that we have, and then subtract a plugged into the function that we have, and then divide it by b over a. So when we go ahead and do that, let's erase this because we don't need it anymore. So when we go ahead and do that, we're plugging in b into this inverse composition for x, right? Let's use a highlighter again. So we go in top, we have b over ac minus d over c minus uppercase b over ac. Be aware that the lowercase and uppercase a's and b's are not the same. Minus what happens when we plug in a to that same exact function. A over ac minus d over c minus b, capital B over ac, and then all over b minus a. Now we need to simplify one thing that's really nice about this, because we're finding the average rate of change of the same function, we have to distribute this negative. And when we do that, notice, let's use a red highlighter here, that this negative d over c is going to cancel with a positive d over c, right? I can make this negative. And then the negative b over ac is also going to cancel with the positive b over ac. So let's see what we got here. We got b over ac minus a over ac, all divided by b over a. Or sorry, b minus a. Let's make a divider here. Okay, so that's where we're at. Now let's put this back in purple. We have b over ac minus a over ac over b minus a. Well, we have some common denominators here, which is going to help us simplify in the numerator. And remember that when you are dividing a fraction by another fraction, you can rewrite it. So this is our numerator with the common denominator as it's multiplying by the reciprocal, right? So if this was over 1, we could multiply it by the reciprocal, which, oh, look at that. That's awesome. They cancel, and your final answer is that the average rate of change of the inverse of f of g of x is 1 over ac. Simplifies really nicely. Okay. So now, moving on to part B, it's very similar. You can see the similar wording, right? We're finding the inverse of g of f of x. So now we're finding the switched, not the inverse, the switched composition, g of f of x. And then we have to find the inverse of that. So go ahead and pause the video. Give this a practice on your own. All right, let's go ahead and check it out. Hopefully you tried it. Here's the work. So again, we first have to find that composition function, g of f of x. That meant we plugged the f function into the g. By doing that, we got this. And then from there, we have to find the inverse of this composition function. When we did that, we got here. And then again, as we mentioned before, you're not done at that point. We're finding the average rate of change of the inverse of composition function g of f of x. So then that would be the blue, plugging in b minus what happens when you plug in a, all divided by the difference of the two x values on the interval. Okay, simplify. What we do notice is something that's pretty cool, that the inverse, the average rate of changes of the inverses, of the flipped composition functions, they did happen to be the same, which is pretty cool. Okay. So a lot of your homework tonight, again, some of it might be review from Algebra 2, just dealing with linear functions, as we saw earlier in these notes. Some of it you might have to use your calculator. Some of it you don't need to use your calculator. Just make sure you're double checking your work, being very careful, because as we get these longer, and we're going to notice we're going to get a lot longer equations, being careful with the negatives and canceling out when they should or they shouldn't are going to become really important. Okay, let's go ahead and try the homework, and good luck.